In this video, we will prove the composition property of differential privacy. Assume that M is epsilon M delta M differentially private and N is epsilon N delta N differentially private. The composition property can be stated as follows. Let the mechanism L that takes as input a database and that returns a reply to M and a reply to N. Let's consider this mechanism that returns the replies of both mechanisms run independently. Then L is epsilon M plus epsilon N delta M plus delta N differentially private. In other words, when we extract information from a private database using differentially private mechanisms, then the losses of privacy measured in terms of epsilons and deltas add up. This very appealing property is one of the key selling points of differential privacy. Now, I should say that there's an even better differential privacy guarantee, but it is vastly more technical and harder to prove. And I guess for most purposes, this addition of differentially private losses is quite a nice theorem to keep in mind. In particular, if you have a private database such that the only accesses to this database require monitored differentially private mechanisms, then you can derive from what mechanisms have been applied and how many times they have been applied the total privacy loss of the private database. In particular, if you delete the entire private database afterwards, then you know for sure the total privacy loss of the private database over all of its lifetime. Let's now prove the composition property. To do so, consider two neighbor databases X and Y. We shall use the interpretation of epsilons and deltas we proved in a previous video, namely saying that M and N are differentially private and run independently means that there exist two events breach M and breach N and two random variables Zm and Zn such that the probability of a breach M is at most delta M. The probability that M of Y is in Sm, given that there's no breach of M, is equal to the probability that Zm is in Sm, given that there's no breach of M, and the probability of Zm in Sm is epsilon differentially private with respect to M of X. That is, it is at most e to the epsilon times the probability that M of X is in Sm. And similarly, we have the same constraints on breach N and Zn. Now we are going to assume that anything that has to do with M and with N are independent, like the two runs are completely independent from one another, the two events breach M and breach N are independent, and the two random variables Zm and Zn are independent. Now let's define the event breach to be the union of a breach of M and a breach of N. Combining it all leads us to the equality. The probability that M of Y and N of Y are in Sm times Sn is equal to the probability that, so I'm going to decompose it into the event where the breach happens and the event where the breach does not happen, and I'm going to add two additional terms that cancel each other out, where the Zm and Zn appear. Now crucially, M of Y, given that there's no breach, behaves exactly like Zm and similarly for N of Y. And this means that we can collapse all of the first terms into the probability that Zm and Zn are in Sm and Sn. Meanwhile, the other terms that can be factored by the term probability of a breach, and all the terms that precede it is necessarily at most 1. So eventually we get the inequality that says that the probability we were concerned with is at most the probability that Zm is in Sm times the probability that Zn is in Sn plus the probability that there is a breach. And these two probabilities here are epsilon M and epsilon N differentially private, which means that these are at most e to the epsilon M times the probability that M of X is in Sm times e to the epsilon N times the probability that N of X is in Sn plus the probability that there is a breach, and this is at most the probability that there's a breach of M plus the probability that there's a breach of N. So if you wanted the whole formula, there should be a minus the intersection of the probability of the intersection of the events, but this is an upper bound, so we can remove the minus term. And eventually we retrieve e to the epsilon m plus epsilon n times the probability that m of x and n of x are in Sm times Sn plus delta m plus delta n, and this corresponds exactly to saying that the mechanism L is epsilon m plus epsilon n delta m plus delta n differentially private QED.